Hello everyone, this is Singh 𝐒𝐲𝐬𝐭𝐞𝐦 and today I'm back with another video in which we will be discussing the final chapter of Designing Data Intensive Applications book. So I have already covered 11 chapters, the summary of them, and this is the final one, the 12th one, and the name of the chapter is The Future of Data Systems. So let's quickly close this and then we will be done with the book. Okay, so as I said, the name of the chapter is The Future of Data Systems. It basically talks about ideas and approaches that can improve the ways we design and build applications. Okay, so let's start with the first topic, which is data integration. Now, every solution you choose for a problem has pros and cons. Okay, it has some trade-offs. There are some benefits, there are some disadvantages, there are some advantages. Okay, so we choose based on whatever works for our use case. Okay, so appropriate tool choice of tool depends on circumstances, your use case, business problem statement, and depending on that we choose that. Okay, this is what makes sense to our use case, so let's go ahead with this particular solution or technology or whatever we are trying to solve at that particular point of time. Okay, combining specialized tools by derived data. Okay, so whenever we try to choose a solution, right, and we are talking here about data systems mostly, so a single system, a single tool or a system might not be able to solve all the problems, so you might need a combination of multiple tools. Okay, uh, let's take example of databases. You have different kind of databases. You have relational databases, you have search kind of databases, you want to store some kind of caching capabilities, you want to have some kind of analytics capabilities, so you have different kind of problem statements. Okay, and there are different databases which are built for different of these use cases. So it is very well true that what one person considers pointless feature might be a very much important feature for someone else. Okay, a product or a company might be built on analytics on top of analytics database. Okay, but some for other company that is irrelevant requirement. Okay, so the idea is that you will have to do that analysis, you will have to do that trade-off analysis, you will have to figure out what are the pros and cons for you for according to your business problem statement, and then choose accordingly. Reasoning about data flows. So same data is stored in different stores for different access patterns. This we already discussed. Different product problem statements we choose based on that. You need to be clear about input and output. What's the source and destination for the data? So let's try to understand this with the help of example. So let's say you have this relational database, and you also want to store this data in case in the search index, let's say Elasticsearch, yes, and to provide some kind of search filters on top of it. Okay, and you are using CDC. If you don't know, it's change data capture. We have discussed in this book series as well as there is a dedicated video on CDC where we talk about what CDC is and how it is implemented basically. Okay, so let's say you are using some message broker such as Kafka to implement this CDC, so that whatever being pushed in the database, it is also stored in the Elasticsearch cluster. Okay, this is the simple idea. Now what I mean from this statement is you should be clear about input and output. Okay, where this what's the source of the data. So let's say for this relational database, the data is coming from some processing, some state change, state modifications happening in the application code, and from there the data is being stored to the database. Okay, so this is input to this, and then output is stored into this database. Okay, this is the source here and this is the destination. But for this Elasticsearch cluster, the data is moved via CDC. Okay, so for this the source is the relational database and then the destination is the Elasticsearch cluster. Okay, so you have to be clear about what is your source and what is the destination of the data, whether it is derived data or your first class data. Depending on that, you store that. Derived data versus distributed transactions. So in case of distributed transactions, they are helpful to keep the data consistent. Okay, generally in sync or atomic operation. So even if there are multiple databases involved, you try to store the data in sync or in a single consistent or atomic operation. Okay, either it's saved all the databases or it is not saved at all. Okay, but in case of derived data, we generally write it in a asynchronous fashion, that the data is pushed to this relational database, and then once it is here, we publish some kind of event. CDC is a popular way to achieve it, and then it is asynchronously saved to our Elasticsearch cluster as well. Cool. Combining specialized tools by derived data. So for one of the use case we discussed, right, we can have integration of OLTP-DB plus full text search index for arbitrary keyword search queries. The use case which we discussed right now here as well. Combination of relational database plus Elasticsearch cluster. And for simple applications, PostgreSQL full text ingestion feature can be used as well. Now the idea here is, we discussed, right, every solution to a problem has pros and cons. There are trade-offs. So if we have a simple use case which can be solved by, let's say, relational database search functionalities as well, so let's try to leverage that. Okay, if you don't have requirement to use Elasticsearch, or like you don't want full-fledged search index system, then go ahead and use it with the PostgreSQL. That solves your use case, then go ahead with it. Okay, search indexes are generally not used as durable system of record. This is just information for sure. One person might consider something as pointless. We already discussed this. I think so. Yeah, it is here. Okay, so the limits of total ordering. So we have discussed what total order broadcast is, what total ordering is in one of our previous videos, and the relation with causality of total ordering. So if a system is small, construction of totally ordered event log is relatively easy. Okay, and it's not just with the total order broadcast or total ordering. It is true for anything which you are trying to achieve. Okay, it's easier at lower scale to have some implementation in place, but there are certain limitations with scale. What are the limitations? All the events should pass via a single node which decides the ordering. This has to be ensured. Now, let's say that single node might not be able to handle it. So if that happens, you will need to partition if single machine can't handle the volume. So you will have to create those partitions in place, and then the ordering will be ensured among those partitions. And if the servers are multi-region, that's another hurdle which you can encounter, that the servers are multi-region. So if that happens, then there can be network delays. Which can make synchronous coordination inefficient, and it can lead to undefined event ordering. This can happen, right? There are nodes which are in the multiple regions, or your partitions per se are there. They are in the multiple regions, and then it can cause issues. Cool. In case of microservice architecture, let's say you have multiple services. Now if you have multiple services, it can very well happen that two events are generated by separate services, and then it's hard to figure out what's the actual order of those events. Okay, so that's the another problem. So how you try to achieve it? Well, you can use consensus algorithms, but total order broadcast work well with single node. I mean, like, both the consensus algorithms as well as total order broadcast work well with a single leader node. It becomes really difficult if there are multiple nodes, either they are in same region or multiple regions. It definitely becomes difficult in those scenarios. Ordering events to capture causality. So causality also we have discussed in our previous videos. Basically means that you have some cause, and according to that cause there is some effect. So let's take some example. Okay, so if there is no causal link between events, lack of total order is not an issue. But if there is a causal link, that if this happen, then this should happen, basically cause and effect. Okay, so how will you handle it? So let's take an example of Facebook. So on Facebook there are two users. One is Mandeep and one is some. Okay. So Mandeep and that some person were in relationship, and then they broke up. Very sad. Very sad. Okay, so due to that breakup, that person is posting something about Mandeep, that this Mandeep is very bad person, and he has also wrote a book called Systems and on AWS. So don't check it out. Some bad stuff. Okay, what the system has to ensure is that since that person has befriended or unfollowed Mandeep, uh, Mandeep should not be able to see that post. Okay, so that's the idea of it. That's what we want to do. Okay, now let's say if there are separate system for messaging and friendship. Okay, there are separate system for messaging, who manages those messages, who manages the friendship or relations, right? So the ordering of event can be lost, that which happened first, like you made the post first and then you befriended, not befriended, unfollowed, or you made like you unfollowed first and then you made the post. So the event, the multiple microservices use cases, right? So it can, the ordering can be lost. Okay, message event is processed first and then unfriend event later, so this can happen. Notifications can join between messages and friend list. Okay, so the idea could be that you can use either logical timestamps. We have discussed logical timestamps as well in our previous videos, but yeah, so you should definitely check out the entire playlist so that the terms which are coming here, you are able to understand them. So the recipient should still have some handling for out of order events. So either the handling should be at the recipient level, that what's the current status right now? Is the person still following that person to which the post came? Okay, so either the handling is placed at the recipient end. You can log an event to a record. You can log the event to record state of the system to assign a unique identifier. This identifier can be used to record causal dependency, that what's the dependency between those two events which are happening. And you can definitely have conflict resolution algorithms to handle any kind of these scenarios. Okay, let's move to our next discussion, which is batch and stream processing. We had chapter 10 as batch processing, we had chapter 11 as stream processing, and this chapter 12 we are discussing kind of both. So out of output of batch or stream processing are derived data set basically. Okay, you have some kind of data present, and then you are running some kind of workflows or anything, any sort of jobs to generate a derived data set for any of your use case what you have. So Lambda architecture is one of the approach. You try to combine both this batch and stream processing together. Okay, so you record the incoming data, append immutable events to dataset. So this is basically a log entry, events coming up, and then you keep on appending to this immutable data set. Generate read optimized views from the events. You try to generate read optimized events from views from these events, so that your user queries can be served very quickly from this views, materialized views which are generated. Okay, this architecture paradigm proposes two systems in parallel. So you have two systems, one is batch processing system, another one is stream processing system. Okay, so batch processing system can use map reduce, some sort of map reduce. Okay, it consumes the events and produce correlated version of derived view. And the stream processing system such as Storm, a Storm is much similar to, I mean, as there are multiple. So Apache Storm, Apache MapReduce, Apache Sparks, all these are under Apache Foundation. But yeah, it can be used for stream processing. It consumes the event and produces approximate update. Okay, approximate update of the view. So the issue here is with the Lambda architecture is there is additional operational overhead. Okay, when I say operational head, it basically means that you are trying to manage two systems at the same point. You are trying to manage batch processing system. You are also trying to manage the stream processing system. Okay, operation output from separate system is combined for user request. You are trying to combine output from two systems. Now, if the data set is simple, or like the join operation is simple, then it's easy to do. But if there is complex join required for combining the data from these two systems, it's really hard. Okay, so then the handling becomes hard. So what you can try to do is you can try to unify the two systems, and the system need below features. First is it has ability to replay historical events. The second is exactly one semantics for stream processors, and then tool for windowing for event processing. So the idea here is basically like if I want to get events from yesterday, I should be able to get it. Even if I want to specify, let's say a time frame, let's say I want to get for yesterday's event in that 1 hour time frame. So I should there's some kind of windowing approach. The idea here is that you don't have to replay all the historical events. If you want to get historical events, you can specify some sort of window, and then you can get the events from that window specifically, and then you can run the processing. So that's the idea. Next topic is unbundling databases. So let's start with thinking of differences between Unix and databases. Now, if we talk about Unix, it operates on top of files, right? So you Unix is a thin wrapper on hardware resources such as files. Okay, there are other resources, but yeah, let's talk in terms of storage because we are comparing with the we are talking about data systems, and we are trying to compare it with the data systems. Okay, so Unix is a thin wrapper on hardware resources such as files, but a database is higher level abstraction. User don't have to worry about implementation details. So in case of Unix, you have to think about how the data should be stored in the file, so that you should be able to retrieve it easily. You can dump anything. There is no structure defined. But in case of databases, there is some sort of structure through which, or like by which you specify like how your data is stored, and then you can retrieve that easily. So there is a higher level abstraction, but yeah, depending on the use case, we do it. Creating an index, this is a small topic which is there in the book, but yeah, so the idea here is let's say you want to create the index for existing data. So your table is already there for that particular database, and then now you want to create an index. So if you want to do that, what you do is take a snapshot of existing data and then store them in the index in the sorted fashion, whatever the indexing strategy is. Okay, so the data is stored. and then it is definitely compute for any new data which is added there. Meta database for everything. So super database we are talking about. So let's say you want to design a single database. Okay, so the it's hard for a single database to solve all the use cases. We talked definitely we talked about that in the beginning as well, that we choose database depending on whatever requirements we have, right? So how will you choose that? How will you specify that? How will you figure out that? Okay, so let's say you want to unify the reads. Okay, so there are two approaches here. First is federated databases, second is unbundled database. Okay, so in case of federated database, what we're trying to do is, let's say you have multiple databases. Okay, you have relational database, and then you have a search index. Okay, so you want to unify the read, so you have a single interface through which user interact, and it could be much similar to GraphQL. Okay, GraphQL federation. So you might have heard about that GraphQL federation. Okay, or like AWS, you have AppSync. I think it offers that functionality as far as I know. So the idea is you're trying to unify the reads in between the different databases which you have. Okay, and in case of unbundled database, you are trying to unify the reads. Okay, so you're trying to synchronize the writes among underlying database stores. So you have multiple data stores, and then whenever the write operation is happening, you're trying to maintain that synchronization between those database. Okay, so how will you make that unbundling work? So the first idea could be that you have distributed transactions. Okay, distributed transactions, when I say, so for these two databases you have transaction T1 and transaction T2. Okay, so the idea is that both the transactions should succeed, so the data is committed to both of them. If it is fails, then it fails in both of them, so it's an atomic operation. Okay, but the problem here is every system has a different transaction semantics, so distributed transaction could be hard, and it could also be possible that there is no data transaction functionality which is offered by their database, so it becomes more hard. So how will you do it? So it's actually it's hard problem to solve. Okay, this might not be a good approach for transactions spreading multiple data stores. I totally agree that it's a hard problem to solve. So is there really need to solve this problem first of all? Okay, okay, great. So the practical approach could be you have a async event log with idempotent writes. Idempotency, we had multiple videos which we have discussed, and mostly in terms of payment processing. But the idea with idempotency is that if the request is sent multiple times, okay, the same request is sent multiple times, it is only processed once. Okay, and you get the same output, so there is no, the mutation is occurred only once. Okay, and it also ensures, if you have that, there is also a loose coupling between the components. Earlier you were trying to combine these two transactions together, there was coupled. Okay, there was, we are trying to create that atomic operation, but now they are loosely coupled, so good thing. Unbundled versus integrated systems. So complexity is high for managing multiple infrastructure. There is learning curve involved, there is operational overhead involved. If you're trying to manage multiple databases, then there is extra operational overhead which is involved there. So if it's possible to create a single integrated software, then it could be easy to manage. Okay, and if feasible, we can try to use single software for multiple use cases, as long as it serves your use case. You don't have to think of too much scale in the beginning, you may never reach there. So that's the idea of it. Okay, we discussed one example that if we are able to solve our search use case with the help of Postgres, then don't think of scale on day zero, that you will have such a large scale, you will need to solve all those, this filter, that filter, and all those, and then you introduce a search cluster in the on day zero. Okay, you don't have that requirement on the day zero, so skip that. In future, if there is a requirement, then you can choose that. So that's the idea of it. Designing applications around data flow. So how like, if we talk about the modern applications, you mostly see is stateless application. Okay, there are very less stateful applications which are there, very few. Okay, so application code is deployed with tools such as Docker, Kubernetes, or whatever tool are using, and database is used as a durable storage for that application. So you have this stateless application, and then the data or the state is stored in a durable data source, it's Postgres or Dynamo or whatever database you are using. Most web applications are stateless, and the benefit of that is you can easily add or remove servers because there is no state which is maintained on those servers, so it's easy. Okay, so data flow, interplay between state change and application code. So application code respond to state changes by consuming events. So whatever the events are happening, the application code can consume those events, consume those requests, and then accordingly they can make the state change in the database, associated database. Okay, stream processes, stream processors and services. Let's try to compare them. So a customer is buying something priced in USD but paying in INR. You need currency conversion logic. Okay, you are trying to buy what system design on AWS. It's a great book by author Mandeep Singh Shekhawat and Jayant Kumar. So you are trying to buy this book on Amazon.com. Okay, now I'm an Indian user. Okay, so if I'm trying to buy this book, I will pay in INR, but the book is priced in dollars. You can, if you're in India, you don't have to buy on Amazon.com. Basically, you can buy on Amazon.in as well. But let's take for the discuss for the sake of example. So you're trying to buy this book, system design on AWS on Amazon, and the price, it's priced in the USD, okay, American dollars basically, and then you will pay via INR. So your application, Amazon, we are talking an example. So Amazon will have some requirement to have that currency conversion logic. Okay, so there are two approaches basically. First is you have microservices. When I say microservices, so you have your order placement service, okay, or your payment processing system, which talks to this exchange rate service, okay, to get the currency rate. Okay, so this is the currency rate right now, so accordingly I will charge the customer. Okay, the other approach could be data flow approach. Now in this approach, what's the idea is, this payment processing system, okay, or your order placement service subscribes to the stream of exchange rate updates and keep a record of exchange rate in the local database. Now if this happens, what actually it ensures is that you have that local copy in place. You don't have to call this additional exchange rate service to get the data. Okay, so the data flow approach is faster. Why it's faster? Because you don't have to call that additional service. You have that conversion rate in place in the local copy or local database in place. So great. Okay, and it is also more robust. Why it's more robust? Because it is independent of failures of another service. If another service is available, not available, I don't care about that. I will have the data in my local database, so I can directly use it. Okay, local database, local cache, whatever data store you are using, I have that data, so I can use it. You can also treat, so another moving to another topic, reads are events too. Okay, so you can also treat reads as events. Now when it makes sense, like to make our requests treat as events and then respond into the stream processor as the output. So generally write requests are seen as events, but you can also treat read events, reads as well as read as well events. Okay, read event goes to a stream processor that this is my read request. Okay, and then processor emits the result to the read to the output stream. So you have this read requirement, this is the data for this read request, basically read event basically. Okay, now multi-partition data processing. So if the queries are touching single partition, then event, this approach could be overkill. But if let's say my if my data is present in multiple partitions, then this approach could be really useful. Okay, so that's the idea of it. Okay, so let's talk about aiming for correctness. The next topic is aiming for correctness, how you can ensure your data is correct in your system. Okay, the entire data systems you are managing, how you can ensure all that. So for databases, um, if you think around any solution which you are using, okay, let's say you have multiple components in your architecture. So just because your database has safety properties such as serializable transactions, the issue can still happen if there is a bug in application. Okay, so let's say this is my app and this is my DB. So my this DB is great solution, but what if this application is faulty, there is bug in this application, so it can still write bad data or it can delete some correct data. Okay, so the issue can happen. So there are few ways through which you can ensure that, or you can try to avoid these kind of scenarios. One, first is exactly once execution of that operation. So processing twice is form of data corruption. If the request is already processed, so you should not process it again. So idempotency is one of the way to overcome this. Another way is duplicate suppression. Okay, you suppress those duplicates. So let's take an example of how TCP does it. So TCP use sequence numbers to figure out lost or duplicated packets. So it use those sequence numbers. If the packets are lost, then it retransmit those packets. If there are duplicates, then it removes those duplicates. Let's talk in terms of database connection. Okay, so transaction is tied to a client connection. So this is your app. Again, let's draw it for easier visibility, and this is your DB. Okay, this is your client connection. So this is your TCP client connection between application and database. Okay, let's think about a scenario. Okay, let's say it sent a request that commit, but before receiving the response some issue happened with the application, and this client was never able to figure out if that operation was committed or aborted. Okay, so that's the problem. So client can retry, but it's outside the scope of TCP duplicate separation now, because it's a new connection. Okay, it retried, but it's a new connection now. It doesn't know what happened with that. Okay, so it becomes out of scope for that TCP handling, TCP separation logic, and the duplicate separation logic basically. Okay, so you can try to use two-phase commit, okay, as a one-to-one mapping between TCP connection and transaction. But is this enough? No. What if connection issue between user and application server? This can also happen. Okay, you ensure that this works properly, but this is a user. The issue can happen here as well, at this part as well. The request can drop. Okay, user was establishing the connection. This happened correctly, but it this request dropped, so the user tried again. So what happened in this scenario? So uh, the duplication still happens. So what you have to ensure is that if you have multiple components or multiple actors in your data system, then you have to ensure that your uh, uh, this handling is placed at each and every architecture or like component level. Okay, so you have to consider end-to-end flow of the request. You let's say generate unique identifiers such as UUID, which is sent across the components, and then it is used to figure out if the data was already processed or not. Okay, great. We have to apply end-to-end thinking in the database system. So you need end-to-end solution to fix the problem. One component handling it really well don't solve the problem. So that's the idea of it. The final topic is doing the right thing. So every system is built for a purpose, and every action has consequences. Whatever you are choosing, it has some unintended consequences. It has some intended consequences, which we already know. Okay, so pros and cons kind of things, trade-offs kind of thing. Okay, so few things. Predictive, what do I mean from predictive analysis? Predictive analysis, data analysis to predict weather. So this is one of the example. Okay, so you want to analyze something. Okay, now based on the data which you are running some algorithms, or you have some humans in place who predict something, predict whether, or let's say you have to approve a loan or reject a loan for a user depending on some data you have. So there is some bias and discrimination involved, both in case of system is doing this based on past analysis. What if that past analysis is wrong? So the machine or the algorithm will give wrong output. A person was really needing the loan, but machine suggested that this person is faulty person, but he was not faulty person. So there issues can happen. Same goes with the humans as well. Or discrimination process, feedback loops. You can also try to ensure that there are machines as well as humans work together to achieve some output. So there can be feedback loops in between, that you verify whatever output was generated, and then you use for the future tracking as well. Similarly, the next thing is privacy and tracking. So we are in like data systems, right? So whatever data we are managing, we always try to get the consent of a user. Okay, what if there's a user personal information, you have the consent that okay, you can store this information, I can process this information, I can take actions, or I can derive insights from this information. So all those things. So you should have consent of a user, privacy and use of data, how you are trying to use that data. Okay, uh, who all users can access that data. Okay, so that kind of thing. Data as assets and power. So you should use data as an asset and power, not in the reverse way. And when I say power, power in the hands of user. Okay, cool. So this is all I want to talk about in this is the final chapter. So yeah, the playlist will be over after this video. There are 12 chapters. Consider subscribing the channel MsDeep Singh if you like the videos, if you learn something new. And this is my O'Reilly book Systems and on AWS, which I just shown you multiple times in this video. So consider checking it out if you want to learn system design and then how you actually build systems on AWS. So consider checking it out on the O'Reilly platform. You can explore it via free trial, and then if you like the book, then consider buying as well, and you can buy it on Amazon worldwide. So stay connected. We will learn more things in upcoming videos. Till then, stay safe. Bye.